Hello. So in the last video we calculated the reflection and transmission coefficients using the definition of current density. Okay, so today we're going to try and find A, B and C, which are of course constants. So how do you figure out the constants? You do this as you did in the, remember the series on the infinite square well, we used boundary conditions, okay? However, here you can't necessarily say that psi x goes to 0, okay? Because the potential is no longer infinite. Instead, the boundary conditions are that psi x, okay, and the derivative of psi x, okay, are continuous across the potential steps boundary, okay? These are the boundary conditions, okay? In other words, if they're continuous, we're going to get psi 1, 0 is equal to psi 2, 0. Okay, that's our first condition. And the second condition is that the derivatives also are continuous. Psi 1 dx 0 equals d psi 2 dx 0. Okay? Brilliant. So, obviously, you know the following, okay? Remember from the last video, okay? Commit that to memory. X is less than 0, we get that. X is greater than 0, we get that. Okay? So, therefore, plugging these two equations into psi 1, 0 and psi 2, 0, okay? What we'll get, plugging these two equations, we're simply going to get psi 1, 0 equals psi 2, 0. It's going to give us A plus B is equal to C. Yeah? A plus B is equal to C. Psi 1 is equal to psi 2. Okay? And plugging into this second boundary condition with the derivatives, you plug that into the condition you have here, it's going to give us K1A minus K1B is equal to K2C. Okay? That's what we get. Right. So you can solve for B in terms of A. Okay, so it's very simple algebra, just rearranging the formula. So if you solve for B in terms of A, okay, we're looking at obviously this here. If you solve for B, you get that B is equal to K1 minus K2 divided by K1 plus K2 multiplied by A. Okay? And you can solve for C in terms of A. Okay? If you solve for C in terms of A, I'll write this up. Let's just say we write it here. And C is equal to 2K1 plus K2. Okay, there's no need for me to show you how to rearrange, okay? We all know how to rearrange algebraically. Alright, and that's what you get for C and B. Okay, so you can calculate A from the normalization condition of the wave function. Okay, if you remember, the normalization condition in the infinite square L series, we got that 1 is equal to the integral of psi of x squared dx. Okay, but you don't actually need A, okay, because it drops out of the ratios for reflection and transmission coefficients, R and T. Okay, remember, R is equal to B squared divided by A squared. That's what we did in the last video. And we had T is equal to K2 C squared divided by K1 A squared. Okay, and we don't need A because they simply cancel each other out. R is equal to K1 minus K2 squared divided by K1 plus K2 squared. Okay? Simple. And of course T, do the same thing. T is equal to 4k1 k2 divided by k1 plus k2 squared. That's what we get for transmission and reflection coefficients. And there you have it. We have just calculated transmission and reflection coefficients. Now let's just inspect what we have here. So it's actually an interesting result, and it disagrees with classical physics, which says that there should be no particle reflection at all. Or you can see, okay, if K1 is not equal to K2, okay, K1 is not equal to K2, okay, then there will be indeed be particle reflection, okay? If K1 is not equal to K2, there's obviously going to be particle reflection. If they are equal, of course, that will just become 0 and reflection will be 0. Note that as K1 goes to K2, R goes to 0 and T goes to 1. Okay? So as K1 is equal to K2, R goes to 0, T is 1, which is what you would expect, right? Okay, reflection is 0, transmission is 1, 100%. So already you have a result that differs from classical physics. The particle can be reflected at the potential step, okay, and it can be transmitted. That's weird, okay, and that's the wave-like behaviour of the particle coming into play again. Okay, and there you have it, mathematical proof for the strangeness of quantum physics. Okay, it can be reflected and it can be transmitted. What's going on? Okay, that's pretty cool, isn't it? Reflection and transmission coefficients. Their A simply cancels out, and you just get in terms of K. Okay? Brilliant. So, there you have it. So, in the next couple of series, we're going to assume that the particle doesn't have enough energy. Okay? Hopefully you know that in this series we dealt where it didn't have enough energy. In the next series, we're going to see when it doesn't have enough energy. Alright, so I hope to see you in the next series of quantum mechanics.